Einen wunderschönen guten Tag zusammen. Mein Name ist Oliver Gastner und heute reden wir über Biocomputing. Und weil Biocomputing so was Internationales ist, rede ich mit jemandem, der französischer Muttersprachler ist, auf Englisch. Also ihr werdet viel Spaß haben. Ja. Hello Fred. Who
Hello.
are you and what do you do?
So, well, I am sitting here in Switzerland, and yes,
In beautiful Lausanne, right?
it's a city small to close to Lausanne, which
Okay.
is called Vevey, and it's also really near the lake.
Okay. So,
So,
so
wonderful
I
place
call it
indeed.
from near the lake, and you're really near the lake, but two different lakes.
I guess. So yes, we're doing biocomputing here at Final Spark. This is a fantastic project that we've been working on since several years now.
Yeah, so let's get us all up to speed. Biocomputing, yeah, like living computers. So give us a little context here, and we're gonna figure out how far you are along this path to a living or to a biological computer, not living computer.
Well, we are at the very much beginning, let's say. I can already answer this. Now, you're right about the wording. It's really critical here because there is no really agreed word for what we are doing. Okay. Some people are talking about wetware computer, and you can find this even in Wikipedia, or biocomputer, intelligence organoid, or organoid intelligence, as opposed to artificial intelligence. So in all cases, this wording implies the use of living neurons in order to perform computation.
Okay. So we have a living nerve cell, yeah, a neuron that is used to transport. Yeah, it's still digital, right? It's not an analog computer, right?
No, it's not digital.
Okay.
And I would even say that it's not really analog. It's close to, no, normally, honestly, it's one or the other, okay? So, it looks, we are using biology. So these are living things, okay? So at the end of the day, you can characterize living things with a number of parameters, which are all analog, okay? And indeed, what we do is processing of information with all these neurons, but these are living neurons. So it's really far away from anything which has been done before, whether it's digital computing, analog computers, or even quantum computers. This is a totally different generation of thing.
Okay. Yeah, at least it's going to be interesting to live through it and to watch your work and how far you get. Now let's figure out where are you at the moment? What can you do? Can you add 2 plus 2 or are you still before that?
Sorry to say that we are still before that, okay? At this point, we're able to store 1 bit of information, for instance, store and retrieve it, of course.
Oh, that's helpful. Yeah.
That's very useful when you store information.
Yeah.
And of course, we are working basically in a path which is quite similar to artificial neural networks. You know that artificial intelligence today, most of it, not all of it, okay, but most of it is based on artificial neural networks. And when you do artificial neural networks, what you try is to teach a system to reproduce, to give some outputs for given inputs. Okay. For instance, I show you a cat, you say it's a cat. I show you a dog, you say it's a dog, okay? So you have 2 answers for different inputs, which are different images.
And if you show me a cat and I say it's a dog, then the neural network gets the feedback that was wrong. Yeah?
It's correct. The network, the artificial neural networks gets the big feedback, it's wrong. And therefore, the connection weights are modified in order to provide the next answer next time. This is how it works in artificial neural network. Somehow, in the core principle, it's not that different in biological neural networks. You still want to provide the right answers for known inputs. And the way to accomplish and to correct the answer is actually to change the weight of the connections. And there is no surprise why it's similar, because the artificial neural networks were actually inspired by biological neural networks. So we are just doing this, and 30 years later, back. Biology to artificial, artificial to biology. This is what we are doing today. So there is no surprise. It's matching.
Okay, if anyone who's listening is wondering why they do it, we'll soon come to that. But yeah, you could say, what's wrong with computers? Yeah, we have them, and they can write our essays and our research papers. So how do you teach a neuron, or how do you give it feedback that it did something wrong or that it did something right?
Well, in a nutshell, I would say we don't know yet.
Okay.
Okay.
Okay, you're still at the point where you say, where you tell a cell, hey cell, it's please store yes. And then you later ask the cell, okay, what did you store? And the cell said yes or no, yeah, 1 or 0. Okay, but you're not connecting the cells already.
Well, no, the neural cells are connecting themselves spontaneously. Okay. This is one thing, which is very good. Okay. To some extent, because if you let them connect randomly, you get a random result.
Obviously, yeah.
Obviously.
Hopefully, our brain cells are not connected randomly, although we sometimes have the suspicion that with some people they are.
So if you learn something really new, you're going to get some random results at the beginning. So it's quite similar. Okay. And it gets to a question, how you are able to modify the synaptic weights in order to get the correct result. Okay. And in artificial neural networks, that's very easy because it's just a number in the tensor. So you modify the number. Okay. But here we have neurons with dendrites and axons and synapses, and there is no direct way to tune each synapse after the other.
Okay, so, for those whose biology lesson has been some time ago, yeah, maybe we give a short description of a neural cell. Yeah, you have the cell body, yeah, and you have dendrites. That's little things that go out from the cell body. Yeah, let me get a. As far as I remember from my biology lessons, that's the only thing I'm trying to remember. So we give them a little reminder on how that works. If I can find a pen, I should be able to find a pen. This works. Okay, so yeah, so you have the cell body. Oh yeah, okay, I have to switch this off. Oh, like this. Oh. Oh, doesn't work. Okay, let's switch this off. Tuck. 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 Okay, like
it's going to come in just
like this here. Yeah, so that's the cell body, and then we have the axon. That's kind of the the cable through which you can transport information like this. And then you have, I think the dendrites go from the body, right? Like this. Those are the dendrites, right? Go from the, I think I have to switch this light off. That's far too bright.
Well, it's okay. Each time you wait a little bit, we see
Yeah,
it.
when I wait a little bit, it's gonna adjust, but this should work. Huh? Yes.
Yeah.
But it doesn't show the dendrites.
Yeah, we see them.
Yeah, those are the dendrites, right? And then the synapses are on the other end, right?
So their synapses are at both ends, actually.
Ah,
On
on
the
both
left
ends.
end
Okay.
and on
And
the
then
right
we
and
always
right end.
draw them as little U's, right? Like this. So, that just that our those who listen to the podcast, you will have to Google for the way a nerve cell looks. But that's mainly the way a nerve cell looks. Yeah, you have synapses on both ends here, and you have the body. You have an axon, and you have those and you have the dendrites on the head and that connect the synapses to the main body like this. So and now say your sentence again. What do you do?
Well, we have to find a way to modify the strength of the synapses in
Mm,
order that the whole network
mm.
does the output that we want for the given input. I
Okay,
show you a cat, you say it's a cat.
instead of manipulating a formula like you could in a digital system, you have to manipulate the working of the synapses in this in the single cells. But how do you
Yes.
address most probably you're going to say we don't know yet, but how do you address
Well,
a single cell? Um,
so just to put in perspective, okay, this is the field of electrophysiology, okay, neural effect, and this has about 40 years of state of the art. Okay, this is not a
mm,
new field at all. Okay,
mm,
what is very new is the idea to use this for computing.
okay. Yeah.
So that means we are not starting from scratch here. There are a
Mm,
lot of work which
yeah.
has been done, and this is called neuroplasticity, how to modify the synaptic connections.
Mm,
And so there are things which are well known that actually you know by experience yourself. For instance, if you don't know how to do something
mm,
and you try by error and trials to make it good,
mm,
as long as you repeat it, you will
mm,
get it better. This you
yeah.
know by experience, okay? There is some theory behind it, which is called long-term potentiation, can explain this, okay? That means with electrical signals, okay, we
Mm,
cannot only give some input or some image, for instance, to our biological network, we can also teach him to do something with the
mm,
right stimulation at the right time.
mm,
So this is how you learn. Okay. When
mm,
I'm telling you now, okay,
yeah.
I'm only communicating with you with actually electrical impulses.
Mm,
This is the only way. And you're still able to learn what I'm saying. It works.
yeah. Okay, now let's as you mentioned the term electrical several times, let's maybe answer that question that we asked before. Why are you doing this? Because you could say, well, we already have that tool. We don't need another hammer. Yeah, that's harder to build, or we don't know how to build this hammer yet. So, what are the advantages to use biocomputers as compared to digital or electrical computers? Or even quantum computers. I think quantum computers use even more energy than normal ones, right?
Yes, I'm not an expert in
No,
quantum
no, I'm
computers,
neither am
and
I.
I'm not sure that actually we tackle the same problems. The same
Mm,
algorithms are not going to be implemented at biological, digital, and quantum computers.
mm,
If we talk about what is the reason of doing this, the primary reason, the most obvious one, okay, is energy consumption. Okay.
mm,
If we take your brain, okay, let's say 100 billion of neurons, this
mm,
is what typical, and you've got about 10,000 connections per neuron. So you multiply these two. And with all these neurons, if I wanted to do a digital simulation on a silicon-based computer of your
mm,
brain, it would take a small nuclear plant.
mm,
Okay. But the reality is that your brain right now, as we are discussing, is consuming 20 watts of power.
mm,
So the superiority of biological computers is minimum 1 million more energy efficient.
mm,
This is absolutely incredible. We live in a world where we are fighting for getting a few percent of better, energy consumption. But this is 1 million factor. This
I
game.
mean, it's rather interesting. I saw a little piece, I think it was done by The Guardian, about Ilya Sutskever, the CTO of OpenAI. And he said at one point, if we have the AI society, like if all the planet is using AI, then every surface will be covered with solar panels, like roughly, that's what he says. Yeah. So especially to operate AI and especially to build those, for example, large language models or other models, you need a lot of energy. So if you could really reduce that factor or reduce the factor of running computers, of computation to be done by the factor of 1 million, that would be very, very interesting. Yeah, because
Yeah.
you could either have far more computing, or you'd need far less energy.
And just know that this is a conservative number, okay? Some people talk about 1 billion less, because there are two things, okay, that we have to distinguish in a cognitive system: how to do something and how to learn something. And in AI, we also make the difference. And there can be a huge difference in energy consumption between training and inference. Okay, so, and the same applies also to biological systems.
So what do you think in a biological system? What's the energy difference between learning something and just creating output?
So this is the miracle in biological system. It seems that training is built in the system. Okay, so it looks like the biological system can learn much quicker. It's not trial and errors are trying to update each of the connection, as I said earlier, for a digital system. It's all together. And just to come back to your initial question, Fred, how are you going to modify these connections? Okay. I'm not saying that I'm telling a solution, okay? I'm just telling one possible direction, okay? That has been examined by others also before. For instance, dopamine is believed to be part of the learning process. That means with a closed loop system where dopamine is released when you succeed in doing something, everything looks like the entire network is able to reconfigure itself for very quickly succeed. Not 1 million or 1 billion of iterations of trial and errors, but very quickly. And you can experiment by yourself. You don't know something, you try, and very quickly you know how to do it. That's incredible.
Yeah, but usually, I mean, okay, but I'm trying with my whole brain, so I'm using all the data that I have learned before, but the single cell, it wouldn't know a whole lot about its environment, right? I mean, it wouldn't know or it wouldn't have the information what other cells have learned or what other groups of cells have learned, right?
Can you reformulate?
Like when I drop something for the first time, and when I drop it for the second time and for the third time, then I know, okay, I need to hold it better so that it doesn't fall and break. Yeah. Or I drop my teddy bear, it doesn't break. I drop a glass, it breaks. And maybe the second time I know. But that's the work of many cells. It's not just one cell that learns something, but it's a whole group of cells that makes that connection. So
Absolutely.
if I only have single cells that are connected to each other, they might not be that quick to form, let's say, a concept. What I can form in my head, I can say, okay, there are soft things and there are hard things and there are breakable things and there are unbreakable things. And when I drop them, the one type breaks and the other usually doesn't. Yeah, if I don't drop them from the Eiffel Tower or something.
But I fully agree that you need many cells, actually. And
Yeah.
this is what we are doing. Okay.
Okay.
In the lab here, just below,
Mm.
we have um, organoids, okay,
Mm.
cerebral organoids, okay, which are made of thousands of neurons, which are
Okay.
connected in 3 dimensions in all directions.
Okay.
And this is what we are using as a
Okay.
processor. So it's not one single neuron. Yeah.
So it's you could call it a mini brain or a nano brain or a
Yeah.
yeah. So how big are those organoids?
So it ranges for the smallest that we use are about 500 microns. So it's a half a millimeter.
Mm.
Okay, you can see it with your eyes.
Yeah.
Okay, in the
Okay. Yeah.
manipulation we do it just with the naked eye. Okay, that's
Yeah.
enough.
Yeah.
The biggest one, which are about, I would say, 4 or 5 millimeter of diameter,
Mm.
so 10 times larger.
Mm.
So you need to get some other problems when you are too big. Okay,
Mm. Yeah,
because
you
you're
need
not
to
able
feed
to bring the
them.
nutrients inside.
Yeah, you need to feed them, you need to access them, and so on.
Yeah.
Well, then let's get to the point of discussion where this is an exception to what I normally do because I usually do not have pre-talks, but we talked for quite a while, and then I said we have to do this again on camera. Um, so let's come to the ethical question, yeah? Because if you create mini brains and if you create these organoids, I mean, we could already discuss about digital computers there um, if they pass the Turing test, yeah, you could say, okay, is it is it a crime if you turn it off? Yeah, because you turn off something that reacts like a human, and can you really tell if you can't tell the difference? Uh, how is that? Yeah, or how? What's the point here? Um, what are the ethical considerations when you talk about those organoids? Are they something like a nano animal or mini animal that would fall under animal protection laws, or what are the ethical considerations that you have in context of your work?
Okay, it's a good question. Just to take back about your scenario of switching off an organoid that would pass the Turing test. What about switching off a ChatGPT version 20 that would pass the Turing test?
Yeah,
Is
that's what my point. Yeah, because some people already talk about these digital statistical output systems, as I would like to call them, as if they were humans. Yeah, ChatGPT, if you ask it something, it says, "I don't know." How does it take? And I'm actually preparing a talk about this. Yeah, like how to talk about AI. Yeah. Um, because my computer doesn't say I. My car doesn't say I, or it's not supposed to, yeah,
yeah.
because it doesn't have a personality. It doesn't have an I, yeah. It doesn't have self-consciousness, and even ChatGPT doesn't, yeah. It can just act as if it had, yeah, or simulate it if you want. So some people might even argue that if you delete if what's it, the New York Times, I think they are suing OpenAI for data that's in there. Now, if you take the data out of the large language model and you have to delete the whole statistical data because you can't take out, I can't imagine how to re-extract what the system statistically simulated. I don't want to say learned. um, and what if you had to delete it? Wouldn't that be, yeah, wouldn't that be deleting or killing ChatGPT 4? Yeah, I don't think it would be. Yeah, but if we make the switch from electrons that go through a mechanical system or electromechanical system, and if we switch to electrons that go through a living system, yeah, so you before you said, yeah, it's a living cell. Okay, then it's life. And as soon as it's live, we have other ethical considerations. And I remember that you last time gave a very convincing answer, but I don't remember it. So I'm going to be astonished again by your cool answer.
Sure, remember myself. But just to say that you said yourself you are not convinced that you would be killing something if you switch off ChatGPT.
But
Okay, this is what
others would be, yeah.
yeah, and I'm asking yourself. Okay, um, think about ChatGPT 10. Okay,
Mhm.
and think about a prompt with which you have will be discussing for hours or years. It will be like a friend to you.
Mm.
Would you say the same thing? We're just at the beginning. So, I mean, the problem of science, it's always blurring the lines.
Mm.
Everybody thinks that it's clear. There is things like this and things like that. And then science comes and say, ah, that's more complicated than we thought. And this is exactly what's happening here.
Mm.
Now, of course, if you consider the number of neurons that we have currently in our organoids, it's about the same as an insect.
Mm.
And I think when you're hitting, I mean, the fly, you're not asking about ethical considerations. So,
Only there are
and if
some
you,
religions that do, but they are very few.
yeah, in general, and generally speaking, if you think about living organisms, even if you are drinking beer,
Mm.
you should be concerned. Okay,
Yeah,
so
killing fungi. Yeah.
so this is about knowing and blurring lines. When you know things that science gives you as a fact, and then we have to live with this reality. How do we, yeah, do we cope with this?
Mm. Okay, now when will we have an organic computer that can run this conversation and steer my screen and connect to the internet and do all the things that my laptop is doing right now? Do you have a timeline? Or no, yeah. Do you have a timeline? It's fine if you say no.
Well, uh, we expect to have something in 5 to 10 years. Okay, um, what the level of sophistication that we will get, we don't know. Okay, it may range from we imagine
Okay,
people who were
just a
inventing
second. I had an acoustic
transistors.
problem. Five to
Yeah,
10 years to which point?
we get something doing something.
Okay, so yeah, a Raspberry Pi or something like that, or a micro, a very simple Platine computer or something like that.
Yes, it may range from a very, I mean, it's not going to be a computer in the sense that you don't program it. Like it's not, you cannot have a sequence of
Mm.
instruction. You cannot
Mm.
program this way, okay? You program it way closer to an artificial neural networks, okay? To make some associations
Okay,
between input and
so it
output.
learns something and then it can react according to the things it learned.
Correct. It can react to things he has never seen before.
Okay.
This is exactly why people are using AI, actually.
Mm.
Okay? Because
Yeah.
it's the power of generalization. Okay,
Yeah.
the power to generalize mathematically is just the power to interpolate. Okay, when you
Mm.
have got 2 points, you guess that in between it must be this.
Mm.
Okay,
Yeah. Yeah.
AI is nothing else,
Mm.
just in more dimensions,
Yeah.
and the same applies to biological computers. So what we will get? So I don't know. It will range between something very simple, a very simple recognition system, or maybe it can be way more advanced. And this I cannot tell at this point.
Mm. So either it can, I don't know, differentiate a triangle from a circle or a cat from a dog or one person from another. Yeah. Um, One face
Yes,
from another.
yes. I'm not sure that we would take the directions of large language model applied to brain organoids. This might be
Mm.
an interesting direction,
Mm.
but there may be other directions that we don't know yet.
Mm.
Just consider that we are discovering a tool like about 1 century ago with semiconductors. People realized that they could do transistors. So, but people who invented transistor didn't think about the internet. So
not really, but the science fiction authors did, yeah, and they already and they also thought about wetware and what we can do with it.
yes, you're very
Yeah.
point on this. I find it incredible that in science fiction the concept of wetware has been around for so many years, actually.
Yeah.
But in science, in real science, it was not. It's incredible.
Yeah, I mean, it was. I'm a Trekkie, yeah, and there were people coming up to the original Star Trek producers, and there are two nice stories that I like to tell at this point. The one is they have these doors that open and close when somebody approaches, and some engineers came to the set and said, "Can you show us how you do the doors?" And then they said, "Yeah, sure, we can show you." Yeah, and there were in the old Star Trek series, there were just two guys on the one and on the other side that pulled back the doors and pushed back the doors together. That was the one thing. But the other thing was that people came from a hospital and they wanted to look at the sick bay on the Enterprise, and they said, "This is totally cool. You have this display up there that shows the vital signs of the person that's lying below there. We want to have a look at that, how you designed that." So that was very serious. Of course, that didn't have a function, yeah,
Yeah.
but they were interested in the concepts. So you read a lot of science fiction now, I hope.
I love science fiction, and with this company, I feel I am living in a science fiction movie, which I've, you watch a movie, science
Yeah,
fiction, really,
yeah,
the movie ends, and then you come back to reality.
yeah,
I found this is an horrible feeling.
yeah.
Okay, so I decided that when I would, I would not stop the movie, and I would live in the movie.
Your science fiction movie never ends. So last time you told me that you were at the current point mainly concerned with keeping those cells alive, yeah, fed and so that they don't die. What's your next? And now you are at the point that you can give it a bite and it's gonna give you back a yes. You give it a yes and it's giving you back a yes. What's your next milestone on that journey?
So first, I'm very happy with the lifetime we get now. Okay, so that was
How
really a
long
huge,
do they live?
well, say several months. Okay, and
7.
several months.
Several. Okay,
Yeah,
several. Okay. Yeah.
we started with a few hours.
Mm.
So I
Yeah,
think it's
that's already
what a progress. So I think
that's a
it's
big progress if you
yes.
draw a line in seconds
Uh,
and yeah.
at this point, I would say we stop working on the lifetime. This is not that critical. We have other problems to solve, and then we'll come
Mm.
back to this later. Okay.
Mm.
The main thing is neuroplasticity. That means how to change the behavior of the network in order to learn something.
Mm.
Okay. And so right now we're working a lot with dopamine and other molecules. In biology, everything is complicated, always. There's no exception. So it's very complicated. And the other problem is that if something works, this doesn't mean that the system works, okay? You just show that something works one time,
Mm.
and this is meaningless, okay? You have to show that it works, I don't know, 10, 50, 100 times, okay?
Mm.
So hopefully we automated everything in our system so we can run automatically 24/7 experiments and make sure something that we observed once can be reproduced. So this is a big pitfall in biology, reproducibility. Okay. So, but I think we are heading in the right direction with this molecule, but it's just the beginning.
Actually, what kind of nerve cells are you using? I've never asked that. What models are you using?
So this is called iPSC, this is called induced pluripotent stem cells. So it works this way. You take some cells of your skin.
Mm.
Okay. From these cells, you are able, according to protocols which have been discovered by Nobel Prize 2005,
Mm.
to regenerate pluripotent stem cells. Okay. So coming from a differentiated cell like this skin cell to a pluripotent stem cells is a process called induction of the pluripotent.
So again, for those who are not so up to date in biology, is a stem cell is a kind of an unprogrammed prototypic cell that can become everything later. Yeah, in former times you used to take it out of fetuses or whatever. That's no longer needed, but it's a kind of an unprogrammed human cell.
Yes, absolutely correct. And the good thing about an unprogrammed human cell is that you can reprogram it to become whatever you want. Okay, that's things that from an ethical perspective, the first impact of this is that in the long term, we imagine that the animal model may disappear from therapeutics trials because we can you can create today organoids, that means small organs reproducing any part of your body, and on which we can test drugs. Okay. Actually, more reliably to some extent, okay, than animals. Okay.
Than with an animal model. So you could make a little heart or a little brain or a little liver or a little whatever.
Well, some people do altogether everything because they want to make sure that if they do a molecule for the brain, it doesn't impact the liver or something else.
Sense. Makes sense. And then from those stem cells, you generate neurons.
Yes, neurons and glial cells. In your brain, there are these two kinds of cells. Okay, there is a hierarchy. I mean, historically, which has been given to the neurons because neurons are spiking. But a lot of work has been done, and there are some other cells which are called glial cells, which people thought were only here to support the activity of the
neurons,
top of the hierarchy, the neurons. But more and more people that these glial cells are maybe way more important than we believed. So there is no hierarchy for us. We differentiate into these two kinds of cells and we keep them in our small organoid.
Okay. Yeah, what else do we definitely need to talk about? No, another thing I'm wondering is how many people are working for Final Spark or at Final Spark?
So right now we are 6 people working here. We have 2 biologists and 4 data scientists like myself. Actually, I have a PhD in signal processing. You know, I don't come from the field of biology, and that's the problem of biocomputing. You have to connect 2 spheres of people which are totally disconnected normally.
Yeah. Okay, then, and is your team about to grow? Do you want to hire? So somebody who's listened up to now, they must be totally interested in maybe working for you. Are you growing your team, or will you be growing your team? When will you be growing your team? Yeah.
So currently we finance our own work. Okay. So that means we are cautious about hiring too many people too quickly. We want to make sure this is going to be a long-term journey. So we have to be cautious about.
It looks like you're gonna take some time, yes.
Yes, but that's not a problem because we have the finance to go like this for some time. Okay. Now there is the two directions: more biologists or more data scientists or more engineers. Okay, to connect actually both systems. So that depends also on the motivation of the people. I think everyone who was hired at Final Spark started by working for free from Final Spark because they were just passionate about the project. And this is personally what I like a lot, just to make sure that people are as motivated as they say. And after some time, if people are really that motivated, say, okay, we have to find a solution actually to formally hire you so we can have a long-term journey together.
Yeah, I mean, money is gonna run out at some point for
Yes.
everybody, depending on the circumstances.
Yeah, absolutely.
And you're
Yes.
not living in an area of Europe that is cheap to live in.
Actually, we are living in the area of the world which is probably one of the most expensive. So, but
Yeah,
but
I was once in Geneva
yeah,
for a short holiday because one of our friends was studying there, and yeah, if you think
but
Switzerland is expensive, go to
it,
Geneva.
it is,
Yeah,
it is. But one good thing is here on the scientific side, we are really at the heart of many things. Okay, two
indeed.
of the main providers of multi-electrode arrays are actually in Switzerland. Okay, and there
Mm,
are maybe 5 providers worldwide. So there is the Blue Brain project, which was at the PFL, just in Lausanne, just the next door here.
mm,
So we have a lot of resources entirely on these topics that we can use.
that's gonna help. So, you don't have to wait 5 or 10 years, but if you have a breakthrough, be sure to drop me a line. Yeah, and we're gonna talk about it, and maybe next time we can even show a little more, so that it's worthwhile for the listeners to also have a look at the at the video.
Yes,
And
actually,
yeah,
you can go to the website. If people can go to the
yeah,
website, they will,
finalspark.com.
yeah,
And
and
I
then
actually
they will
had it
see,
open here. I can
yeah,
show it quickly. I have it open here, and we get a little of an idea what it
if
looks
you click,
like here.
you can click on the live section.
Live, yeah, okay. Oh,
So
you see
if,
your
if
neurons working in real time. I
yeah,
think it's just very slow because of the. Here we go. That's the new version of that there was a very early internet webcam that showed a coffee maker. Yeah, that's a very sophisticated new version of this.
so for me, it looks entirely white. Okay, so here, so these are live pictures and signals coming directly from the lab below in Switzerland. So we have 4 multi-electrode array. This is the first one. And so you see actually 4 brain organoids, which are sitting there with all the electrodes. So this is a picture which has been taken less than 1 hour ago. Picture updated every hour, 24/7.
Okay.
And if you go below, we can see the electrical signal in real time. So this is fed 24/7 real time. So you can see here on the first brain organoids, we have 8 electrodes, and we see that it's very active today, very good. All the electrodes. So, and I see here that maybe we are doing an experiment. Maybe I saw some stimulation signal coming. So
Okay.
these are the action potentials coming from the living neurons.
Okay. And you're picking up the action potential at the axon, right? Or where are you putting
Yes,
them?
yes. Well, you know, this is a bit around a random process because imagine you have 8 electrodes and you put on it an organoid. So you don't know what you're going to end
Ah,
up.
okay. You
But
just put it inside the organoid somewhere, and
yeah,
okay.
and well, on the top of it. And then you see, but if you are in the vicinity of an axon
Mm,
or neural cell, you will catch a variation in the
mm,
electrical field that we can measure.
okay. Yeah.
So this is real things, you know. So if you have contamination, if you have a problem, you can see this. And at the top, you can actually switch between the 4 multi-electrode arrays. There are 4 of them. So it's important to know that we are not the only one working. We have opened this platform to 6 universities worldwide who are now helping us and to work on this problem of neuroplasticity of training. So they are
Mm.
using these neurons, programming them with Python script, and we give free access to research groups. So
Ah, okay.
so that can help.
So
Yeah.
okay, so
So
if you have a research group on organoids or biocomputing, be sure to contact Fred Jordan on LinkedIn, and you're gonna get access here. Yeah.
and this is the experiment with the dopamine that has been running this night. Okay, I'm waiting for new results for next night.
Seems to have it seems to have a break right now here.
Yeah. Right now, it's we are preparing the next experiment for tonight.
Okay.
So it never stops, 24/7.
Okay. Yeah, that's cool. So we finally got something to see. So on finalspark.com you can see the organoids in action. So it's really little like watching a science fiction movie.
Yes, it is.
Okay, Fred, thanks a lot. Liebe Leute, lebt lange in Frieden. Möge der Saft mit euch sein. Fröhliches Biocomputen. Bye bye.
Thanks. Goodbye.